I'm sure you're all well aware of the normal distribution. And it says here the most useful continuous distribution, and the one that occurs frequently, is the normal distribution. So we see the normal distribution a lot in, well, our day-to-day life. And I'm looking at my second screen here. I just did a quick Google search on things that are normally distributed, and just scrolling through quickly here: heights, tossing a coin, IQ, shoe size, birth weight, student's average report. There's heaps of them. So when we've got a normal distribution, we use a particular notation. So if x is our random variable, this means it's normally distributed. This is the mean of the normal distribution, and this is the variance. Okay? So the simplest form of the normal distribution is a random variable with probability density function f with this rule here. So that's the simplest one. So what we'll do is we'll have a bit of a look-see at what that looks like. I'm going to type this into both GeoGebra and Mathematica and have a bit of a look. So I'm going to pause the video now. Okay, so on the screen now you should see the normal distribution curve. So here it is. I've just typed in that function there, and this is what it looks like. Okay, so the classic bell curve. Right, and here it is in Mathematica as well. So I typed in or defined that same function, and I've just plotted that. So there you go. So let's have a longer look at the notes and see where this is going. The normal probability distribution is characterized by a bell-shaped curve, or the bell curve, which is symmetrical about the mean. And it's not approximately symmetrical, it is symmetrical about the mean. The equation of the normal curve is given by this PDF. Okay, so I know that that's different from this one here, because this one is what we call the standard normal distribution curve. This one here is a transformed version, and I'll talk about that a bit more as we go along. So we get a maximum value out of the function at the mean. Okay, so this is the highest value. That's actually the mode, but that's not important for this subject. But it is important to note that the median, the mean, and the mode are all exactly the same value. Many of the frequencies are situated near the mean, so you can see here that like a lot of the values come around the mean. So we get a lot of the values there with relatively few at either end, which is typical of the normal distribution. If we looked at, say, heights of students in year 12, you'd have a lot hovering around the mean, and then you'd have some really tall, some not so tall. What else? The graph extends indefinitely to the right and left of the mean, but never touches or goes below the x-axis, and that's important because that is what a PDF is. The area between the normal curve and the x-axis is equal to 1 square unit. That is, if I integrate the normal distribution curve between positive infinity and negative infinity, the answer is going to be 1. And I want to try that. So I'm just going to try that myself. So if I do dint, and I'm going to do infinity, and then I'm going to do negative, whoopsie, for f of x, for the independent variable x, of course I get an answer of 1. So basically it's saying the area under this curve here, or better graph is this one here, the area under this graph here is equal to 1. Okay, which is also important because that's what a PDF is. Okay, and to get different probabilities between different values, so just say I wanted the probability between -2 and 2, all I do is I just put the -2 and 2 in the terminals and would anti-differentiate this. Don't have to do it, the calculator will do all of this for you to give us the particular probability that we're after. Okay, so let's start with what we call the standard normal distribution, and we use the letter Z to denote the standard normal. So the simplest form of the normal distribution is a random variable with probability density function f with this rule here. Okay, what are its characteristics? Has a mean of 0 and a standard deviation of 1. Okay, now you notice here that we've got 1 there, 2 there, and we've got 3 there. Okay, so we can see that roughly all of the values, or nearly all of the values, fall between 3 standard deviations to the left and the right of the mean. So it's given the standard, the name standard normal distribution. The graph is shown, yep. The probability density function is symmetric around 0, so if you try to reflect it in the y-axis, it produces exactly the same function. So we call that an even function. So we denote it in the following way. So we always call a standard normal distribution Z. We don't have to, but it's convention, where Z is normally distributed, mean is 0, and the variance is 1, which also means that the standard deviation will also equal 1 when it's equal to 1. More on that later. That sounded just confusing, but I'll explain that as we go along. So what we can do is just say what we were looking at, the normal distribution. Just say we had a class that had a mean height of 168, so that was the mean, and the standard deviation was, say, 3. Okay, well, that's not going to fit the standard. So what we would have to do is run a transformation, and this is how we would transform the function. And what we can do is shift the normal distribution to fit basically any mean and standard deviation that we want. Okay, so what I'll do now is I'll show you how this works by typing in the transformed version of it, which is this one right here. So I'm going to type that into GeoGebra now, and I'll show you the results in a sec. Okay, so finally got that typed in, and you can see here what I've got here is my A value is the standard deviation, and my B value is the mean. So what I'm going to do is show you what happens when I move the mean. So all that will do is just move the normal distribution curve horizontally, okay, as far as we want. So it can be a mean of 5, and this is how high this value goes, but we can just extend that out further. Now watch what happens when I increase the standard deviation. So what that's going to do is it's going to increase the spread of numbers covered by the normal distribution curve, I suppose. Now as the spread increases, what will happen is this maximum value here will decrease, and I'll explain why in a sec. So let's just have a look at what happens. So see what happens there. So when I spread out the values, okay, what happens is this maximum value comes down. If I compress the values, let's see what happens there. What happens is the maximum value goes up. Now why does it do this? Well, what it has to do is always preserve an area of 1 underneath this curve. So I can't just stretch it out, okay, and leave the maximum value there, because that means that the area under the curve is going to be more than 1, okay? And that's a problem because we need all of the values, 3 standard deviations to the left and the right of the mean, to be almost 1. So that's what's going to happen there. All right, let's go back to the notes. Okay, so you can see what happens with the different distributions here. So we've got a mean of 0 in the blue one, and a variance of 0.2. Okay, so we get this sort of thin, high curve, I suppose. Here we've got a mean of 0 and a variance of 1. So that means it's this red one here, it just sort of spreads it out a bit more and then lowers the maximum value, and that just is basically what happens. Now notice again, as I change the mean here of -2, it just shifts it 2 units to the left. So our mean here is -2. Alright, so that's if a graph of the normal distribution is dilated and thinner, then the height will increase, and a wider graph will have a lower height. Why? Why is this? To preserve an area under the curve of 1. Okay. Alright, so the only question really we had to do here, on the same set of axes, a calculator can be used to help. The graphs of the standard normal probability density function and the graph of the probability density function of these two. Okay, so the standard, we're going to call that Z, is normally distributed, has a mean of 0 and a variance of 1. So let's put that together as best we can. Now this is a little bit tricky to do. I always find normal distribution curves hard to draw. Okay, so what we'll do is I'm going to go 1, 2, 3, 1, 2, 3. So there's -3, -2, -1, 0, 1, 2, 3. Right, so what we'll do is we'll try to draw this curve. Terrible. Take 2. Awful. Oh, that's not bad. Okay, we'll take that. Okay, so this one here is the Z distribution. Now notice what I've done basically is running the asymptotes or running this back towards the asymptote of the line y equals 0. And what I'm doing is basically matching this graph I drew here, which is that the curve roughly covers 3 standard deviations to the left and the right of the mean. Alright, now let's do a normal distribution with mean 1 and a standard deviation of 1. So we'll call that random variable x is a normal distribution with a mean of 1 and a variance of, this one here is going to be 1. Okay, so all this is going to be, it's going to be this same curve here, but it's going to be moved 1 unit to the left. So let's add a 4 there. And to do this, all I'll do, I can cheat a bit. I'm just going to grab the one I liked and copy it and just move it over 1. Okay, so the highest value occurs there. Let's get it up a bit. Okay, so that there you can see we have that maximum value of 1 and 3 standard deviations to the left and the right. So 3 to the right goes up to 4, 3 to the left goes to -2. Alright, what about the last one? So we've got a normal distribution, we'll call this y is normally distributed with a mean of 1 and a standard deviation of 2. So that means the variance must be the standard deviation squared, so that's going to be 4. Okay, so what's going to happen here is the graph is going to be a bit more stretched out. Okay, so it's going to have a mean of 1, but the standard deviation of 2 means that it's going to go 1 standard deviation, up to 5 is 2 standard deviations, up to 7 is 3 standard deviations. So that's going to be to the right. Then we need to go to the left. So from 1, we've got 2, 4, 6. So we're going to have -4 and -5. Now, the other thing to note is because we're stretching it out, the maximum value can't go to the same point. So I'm going to target a value around about here, and I'm just having a rough estimate. Okay, so there's no way I know that whether that's the height it's going to be, but it's just going to be lower than this height. All right, let's give it a go. All right, this is pretty ordinary, but it kind of meets the requirement here, and that is that the maximum value is lower, okay, than the previous two graphs, and that the spread is greater. All right, so your exercise is 16A, and only a few questions there.